Hello physics students, and welcome to this video all about potential energy. We talked about kinetic energy in the last video. We're going to look in this video at what the difference between potential and kinetic energy is. We're going to look at some different types of potential energy, and then specifically we'll be using calculations to find out more about gravitational potential energy and elastic potential energy. In order to calculate elastic potential energy, we need to understand what the spring constant is as well. So as you all know, the basic difference between kinetic energy and potential energy is that kinetic energy is due to motion, whereas potential energy is stored. It does not involve motion. And the age-old example of kinetic energy happening right here, we have motion. More and more of that kinetic energy, however, is being converted into potential energy. Up here, it's purely potential energy if this bicyclist is stopped right at the top, and on the way down, that potential energy is converted into kinetic energy and the energy of motion. Here are some different examples of potential energy. Elastic potential energy. If we are to stretch a rubber band out or compress a ball, we are exhibiting potential energy, that is being stored elastically. There's also chemical potential energy. That is potential energy that is stored in chemical bonds. Food has a lot of chemical potential energy in it. Gasoline has chemical potential energy in it. Here we have a methane molecule. When it combusts and burns in the presence of oxygen, we have carbon dioxide and water being produced. You guys remember that from chemistry. And that potential energy that is stored in those bonds is being released and converted into mechanical energy to move your car, thermal energy, heat that is given off. We also have gravitational potential energy, and that is the energy that is due to an object's position relative to a gravitational source. In this case, there is gravitational potential energy because of the position of this rock. This rock possesses gravitational potential energy that is going to be proportional to its position away from the gravitational source, which is Earth. We can measure gravitational potential energy using this formula. This stands for potential energy, little g for gravitational potential energy. It is equal to mgh, m being the mass in kilograms, g being the free fall acceleration when we're near the surface of the Earth is 9.81 meters per second squared, and the h is the height in meters. Gravitational potential energy is in units of joules. Kilogram meter squared per second squared is a joule. When we measure gravitational potential energy, we must always discuss the gravitational potential energy relative to some zero level. In other words, the gravitational potential energy of this plant relative to the ground would be different than the gravitational potential energy of this plant relative to this shelf or relative to the shelf it's sitting on. So when we discuss gravitational potential energy, we must always discuss what reference we're using, that it is relative to what position. Elastic potential energy. Now we have a nice little formula for that. We're going to say potential energy and subscript elastic. Elastic potential energy is equal to 1/2 kx squared. Now let's talk about what all these things mean. The interesting thing is that it looks a little bit similar to our kinetic energy, 1/2 mv squared, but we're definitely using some different variables. Potential energy, elastic potential energy is again measured in joules. 1/2 is simply 1/2. This K is the spring constant. And the spring constant is measured in newtons per meter, and it has to do with how resistant a spring is to being compressed or stretched. So here, if we have a spring, we can stretch it out or we can compress it. And this spring constant is a measure of that, how resistant it is to either one of those actions. This x is the distance that it is compressed or stretched. So if we have a problem where we are stretching our spring, the x represents the difference between the spring in its natural state and the distance that that it is stretched. The x is the difference between that distance and then its final distance, because that is the distance that it is being stretched. Or if we're compressing our spring, the x is the distance that the spring is compressed. So it's that difference between what its resting state would be and the final position of the spring. So let's do a sample problem, and let's look at this idea of elastic potential energy in our practice problem. Let's say we have a 70.0 kilogram stuntman, and he's attached to a bungee cord. And that bungee cord, when it is not being stretched, is 15.0 meters long. And this stuntman jumps off the bridge that spans a river, and he is at a height of 50.0 meters. Wow, that'd be exciting, wouldn't it? Okay, when he finally stops, the cord has stretched a length of 44.0 meters. So that means this is the length that the cord has stretched to. It is now this long. Start at 15 meters, but then when it's all stretched out there, it's 44.0 meters. Assuming that the spring constant of the bungee cord is 71.8 newtons per meter, what is the total potential energy relative to the water when the man stops falling? Also, our problem tells us to assume a point mass for the stuntman and disregard the weight of the bungee cord. In case you were going to add those, we're going to disregard those two elements. First, we need to write down everything we know. So here are some things we know that are easy to find: the mass, the spring constant, and the gravity is 9.81 meters per second squared. Next, if we have, make a little diagram here with our bridge up here, our water down here, we have a 50-meter difference between them. And then if we also draw out our bungee lengths, we have the relaxed bungee length is 15 meters. The stretched bungee length is 44.0 meters. So we can look at the height that our stuntman is when he is stretched the length of this bungee cord. He will be at a height above the water, because we're looking at relative to the water here, potential energy relative to the water. We're going to look at his height above that water as 50 minus 44, which is 6 meters. We also want to look at the value of x for the bungee cord. That's going to be the amount that it is stretched here. And that will be the 44 meters of the bungee cord minus the 15, its relaxed state. So x, the value of x for our bungee is 29.0 meters. And one last item to write down is that we know our potential energy when we are at the level of the river. The potential energy here would be equal to 0. So now that we know these things, let's look and see what we're being asked to find. We want to find the total potential energy relative to the water when the man stops falling. So let's go to a new page so we have a little more room to write. So we want to find our total potential energy when the man is at this point, when he stops falling. That bungee cord is stretched this far. He is this high above the water, and we want to know his potential energy relative to the water. So we're going to need to look at his total potential energy, which is going to include the potential energy the gravitational potential energy due to his position above the water, as well as the elastic potential energy in that spring. So we can write that equation right there. Total potential energy equals gravitational potential energy plus elastic potential energy. So let's start with the gravitational potential energy right here. We know that gravitational potential energy equals mgh, our little formula. We can simply plug the values in. We know the mass is 70.0 kilograms. We know gravity is 9.81 meters per second squared, and we know our height, right here, is 6.0 meters. That's going to give us 4,100 joules of gravitational potential energy. Now let's look at the elastic potential energy. Here's our formula for elastic potential energy, 1/2 kx squared and we can just plug our values in there. We know that the spring constant, we're given that, is 71.8 newtons per meter. And we already calculated the x for our spring, it's for our bungee, it's 29.0 meters. Make sure you square the value for x, the 29.0 meters gets squared, and our answer for that would be elastic potential energy of 30,200 joules. We can plug these two values into our equation to find the total potential energy. And when we add those together, we get 3.43 times 10 to the fourth joules. If we go back and we look at our sig figs, we should have 3 sig figs. We get 3 sig figs here in each of these measurements. And actually, I should have added a sig fig to the 6.00 because I shouldn't be limited by that. This also, I could have written 4.10 times 10 to the third joules, just to indicate that I do have 3 sig figs there. An advanced idea, if you want to do something else, how could you set up an experiment to determine the spring constant for a particular spring? How would you go about doing that? And I look forward to seeing what you come up with, and we'll do some practice problems in class.